Hello and welcome to this revision session on stars, which is part of the astrophysics topic in AQA A-Level Physics. So the first thing we're going to look at is classification by luminosity. So when we first observe stars, we look into the night sky. Because all stars have a brightness, they emit radiation. So the brightness of a star is a star's most fundamental property. So when the ancient Greeks first looked into the night sky, they believed they could classify the stars due to brightness. Now all of the ancient Greeks believed that all stars were the same distance away from the Earth. They believed that they all existed on the same shell above the Earth. So therefore the ancient Greeks reasoned that the brightness of a star was due to the power output of the star. So the name given to the power output of a star is its luminosity. The luminosity of a star is the amount of energy radiated out by a star per second. So the luminosity is measured in watts, and our sun has a luminosity of 4 times 10 to the 26 watts. So the intensity of a star is the power received by an observer per unit area. So intensity is power received over area and is measured in watts per meter squared. It is the effective brightness of a star. Now the area of the sphere of radiation emitted is proportional to the separation between the star and the observer squared. In essence, it's the diameter of the sphere squared. So the intensity of a star follows the inverse square law with respect to the distance from that star. So if the energy has been emitted from a point or a sphere like a star, then intensity obeys an inverse square law. This is because the energy spreads out in spherical shells, with the area being 4 pi d squared, where d is the distance from the star. This shows that intensity is proportional to 1 over d squared, proving the inverse square law. So to use the inverse square law, you need to assume that the star gives out an even amount of energy in every direction. So for any star, luminosity equals the total power output, and the intensity is the apparent brightness observed. Now, as a star's luminosity is its total power output at all wavelengths, it's often referred to as the bolometric luminosity. Now, it wouldn't be helpful to catalogue a star's bolometric luminosity for observers to use with optical telescopes. So, when we believed we could classify stars due to brightness, we had an issue because brightness is a subjective scale of measurement. Now, the brightness is a subjective scale because the stars are different distances from the Earth in the universe. The closer a star is to the planet Earth, the brighter it will appear in the night sky. Now, we'll ignore other things such as air pollution, atmospheric distortion, and human interpretation. But the Greeks were unaware of this issue and classified the stars in the night sky based on their brightness as observed from the Earth with the naked eye. And the ancient Greek who did this was Hipparchus. So we call the brightness of a star its apparent magnitude. This means we are only considering the visible radiation emitted by an astronomical object. This is the visible luminosity of a star, which is important that we use optical telescopes to observe objects. Now the apparent magnitude can be measured in watts per meter squared, but Hipparchus came up with his own scale of measurement, and we gave this idea of apparent magnitude the symbol m. Now we are now going to look at the subjective scale, which is completely dependent on Hipparchus's ideas. So we call this the Hipparchus scale. Now Hipparchus deduced there will be a 6-point scale to apparent magnitude. Magnitude 1 would be the stars with the brightest apparent magnitude, and magnitude 6 will be the stars with the dimmest apparent magnitude. Now in the time since Hipparchus, we have amended this scale to be more mathematical because the scale was too subjective to human interpretation. Now it's more important now with our modern measuring techniques that we have a quantitative approach to apparent magnitude. So it's important that we understand that the first magnitude star delivers 100 times as much light to the Earth as a 6th magnitude star. So Norman Pogson formalized this by saying a magnitude 1 star is 100 times brighter than a magnitude 6 star. So a 5 magnitude difference corresponds to an intensity of 100 times. So this tells us that each time we move up the scale, we are changing the brightness by 2.51 times, which is Pogson's ratio. Now this means the apparent magnitude scale is logarithmic. Now we originally assigned Pogson's scale with the idea that Polaris was magnitude 2, but later we worked out that Polaris was slightly variable, so we switched this to Vega as the standard reference, which has an absolute magnitude of 0. Now, you can see here the representation of the apparent magnitude scale, which when you change magnitude, it goes to 2.5 times as dimmer each time. So you can work this out by doing the difference in intensity is equal to 2.51 to the power of the change in the apparent magnitude scale. So what's the difference between 1 and 6? Well, it's 2.51 to the power of 5, because 6 minus 1 is 5, which equals 100. So the 1 magnitude difference is 2.51 times in terms of brightness difference, then 2 magnitude is is 6.25, 3 is 16, 4 is 40 and 5 is 100. Now it's important to remember this change in scale when estimating possible apparent magnitudes of stars in the night sky, yet we've had to further amend the Hipparchus scale in recent years as Hipparchus did his measurements with the naked eye. Now measurements with advanced telescopes can now observe stars with an apparent magnitude greater than 6, and in addition to that we had to further amend this because Hipparchus did not realise that the Sun was a star. So the Sun has an apparent negative apparent magnitude to fit on the scale, as does the Moon, as does Venus. So here you can see the scale of the apparent magnitude, with our negative being very bright and our positive being very dim. So you can see here again the difference in the scale of the apparent magnitude. The lower the apparent magnitude, the brighter the astronomical object in the night sky. The higher the apparent magnitude, the dimmer the astronomical object in the night sky. And the advent of the Hubble Space Telescopes means we can now observe objects with an apparent magnitude of plus 30. It's important to remember that negative on this scale means brighter, so take care when comparing magnitudes. When you say bigger magnitude, do you mean brighter or do you mean dimmer? So it's safer to talk about brighter or dimmer magnitudes rather than larger or smaller. But you can see here our apparent magnitude scale. Now remember, the apparent magnitude is a subjective brightness since it depends on the distance from the Earth. This isn't very useful when we want to compare the power outputs of stars. So we came up with a new property, and this property was absolute magnitude. Absolute magnitude is the brightness of a star if the star was 10 parsecs away, which is 32.6 light years. So the absolute magnitude is given the symbol big M, and it's a measure of a star's inherent brightness. So this means the absolute and apparent magnitudes are measured on the same logarithmic scale. So this means any star closer than 10 parsecs to us would appear dimmer with this definition and have a higher absolute magnitude, and this includes the Sun, whilst any star further away than 10 parsecs would appear brighter with this definition and have a lower absolute magnitude. Now the two ideas, absolute and apparent magnitude, are linked with the following equation: small m minus big M equals 5 log d over 10, where d is the distance between the star and the Earth in parsecs. This is because the definition of absolute magnitude includes the concepts of parsecs. So you can then work out values by using this equation given in your examination book. Now it's important to note that stars which are closer than 10 parsecs have a brighter or more apparent magnitude than absolute. Stars that are further than 10 parsecs have a dimmer or more positive apparent magnitude than absolute, and if m equals m, the star must be 10 parsecs away. So we can see this relationship between the values of the following set of information. Now, it's also important to know that if you know the absolute magnitude, you can use this to work out the distance it is from Earth, which is a method used when a star is too far away to undergo parallax. So here's a sample question. The star Aludra in the constellation Canis Major has the apparent magnitude of 2.5 and is 3,200 light years from the Earth. What is the absolute magnitude of Aludra? Well, the first thing you do is you convert your d into parsecs, so 3,200 divided by 3.21 is 981.5 parsecs. So you can then work it through by popping the numbers in, and you get your answer to be big M equals minus 7.5. So let's look at this concept of absolute magnitude in a bit more detail. There are three main units to measure distances in astronomical objects. The first one is the light year, the second one is the parsec, and the third one is the astronomical unit. Now the astronomical unit is the mean distance between the Earth and the Sun. The mean distance must be used as the distance between the Earth and the Sun varies throughout the year as the Earth's orbit is an ellipse. Now interestingly, the northern hemisphere is closer to the Sun during the winter months compared to the summer. Now we then use the average distance between the Sun and the Earth to determine AU. Now Copernicus defined the concept of the AU but did not know the value of this term. Now the size of the AU was found in 1769 when we measured this during the transit of Venus. Now we know the astronomical unit is now 1.5 times 10 to the 11 meters. The light year is the distance travelled by an electromagnetic wave in a vacuum in 1 Earth year. We use electromagnetic waves to detect the different objects in the universe. So it tells you how long ago the radiation set off from the object. In essence, it's telling you the image of when the object is from. So if an object is 10 light years away, you observe it as it was 10 years ago. So you observe the moon as it was 1.3 seconds ago, the sun as it was 8.3 minutes ago, you observe Alpha Centauri as it was 4.3 years ago, you observe the globular cluster as it was 25,000 years ago, and you observe the Andromeda galaxy as it was 2.5 3.5 million years ago. So this property of the universe allows us to examine the evolution of the universe over time, but it does not allow us to see how the distant galaxies compare in composition to our present day galaxy. So a light year can be worked out, and it is actually 9.46 times 10 to the 15 meters. Now the parsec is the most commonly used astronomical unit, but it is the most difficult unit to define. 1 parsec is the distance which causes a parallax angle of 1 arcsecond to be observed. Now the idea of astronomical parallax is similar to the idea of experimental parallax. An astronomical parallax is a relative change in position of an object due to the motion or angle of an observer. So the distance to nearby stars can be calculated by observing how they move relative to stars that are so distant they appear not to move at all, the background stars. So this is done by comparing the position of nearby stars in relation to background stars at different parts of the Earth orbit. So 1 parsec is the distance which causes a parallax angle of 1 arcsecond to be observed. So consider you are movement and you observe the night sky. So if you have movement, the stars appear to move in the night sky. Now the closer the star is to the observer, the greater this movement. So the near star moves a great deal in this night sky, the far star moves a little in the night sky, and the distant galaxy stays fixed. So the maximum distance which movement can be observed is approximately 350 light years separation. So the stars appear to move in the night sky, and this concept was observed because the Earth is moving around the Sun in orbit. Now we can observe the change in position due to the fixed positions of the distant galaxies. These galaxies are moving slightly due to parallax, but is too small to detect. Now over the course of the year, the stars move backwards and forwards in the night sky as the Earth is orbiting the Sun in an ellipse. So over the year, the following movement is observed. The star will go from position 1 to position 2, then back from position 2 to position 3 again. Now the change in angle observed by the observer is called the angle of parallax. So if you observe the position of the star at either end of the Earth's orbit 6 months apart, the angle of parallax is half the angle that the star moves in relation to the background stars. The greater the angle of parallax, the closer the star is to the observer. Now if we consider the right angle triangle formed over the half the Earth's orbit as shown here, well, we know tan theta is opposite over adjacent, so it's the radius of the orbit divided by the distance between the Earth and the star. So tan theta equals r over d. So here r is the mean distance between the Sun and the Earth, the astronomical unit. So we know that theta equals r over d. Because for small angles in radians, we can use the small angle approximation. So all angles measured in astronomy are less than 10 degrees, so the approximation can be followed, but always state this assumption in your answer. So a parsec is the distance between the Earth and the star when the parallax angle is exactly 1 arcsecond. Now remember, there are 60 arc minutes in 1 degree and 60 arcseconds in 1 minute. So 1 arcsecond is 1/3600th of a degree, as there are 3600 arcseconds in a degree. Now the definition of the parsec must include this triangle showing the different values. Now most examination mark schemes show the definition in this particular orientation. Now 1 arcsecond is an extremely small change in the position of a star from the Earth. Now parallax angles of less than 0.01 arcsecond are very difficult to measure from Earth because of the effects of the Earth's atmosphere. So this limits Earth-based telescopes to measurements of stars of about 100 parsecs away. Now space telescopes can get this to about 0.001, which has increased the number of stars whose distance can be measured using this method. But we've got to use a different method to parallax to measure distances to galaxies, which are about 30,000 parsecs away. Now, we can measure distances greater than 300 parsecs with a method called standard candles, which we'll look at later in the course. Now, there's a shortcut method to working out the distance between objects if you have the angle of parallax. So you know that d is equal to 1 over theta, and this formula works when the angle is in arcseconds, and it gives you your distance in parsecs. Now, you are not given this formula on the examination sheet in your exam. Now, here is the same diagram as shown previously, but in the opposite orientation. The parsec is an important unit because of the way distances to nearby stars can be determined, trigonometrical parallax. So therefore it involves measuring the apparent position of the star against the much more distant background star and how it changes as the Earth goes around the Sun. Now 1 parsec is approximately 3.26 light years. So let's look at an example question using the concept of parallax. A star is in orbit around the Earth with a radius of 6.6 meters. Given that the orbit is 569 kilometers from the Earth, find the angle subtended by it as it is viewed from the Earth. Well, theta equals r over d, so it's 6.6 6 over 569 times 10 to the 3, because kilometers into meters. So you worked out half of the angle subtended in radians. Then you can work out the angle subtended by multiplying it by 2 to be 2.3 times 10 to the minus 5 radians. So now let's look at classification by temperature and blackbody radiation. Now we're used to the terms red hot and white hot when applied to sources of heat, but we're also aware that hot objects emit radiation at infrared wavelengths. This behavior of hot objects and electromagnetic radiation they produce was investigated at the end of the 19th century by Max Planck. Now this is important when observing stars, as all information we get from the stars is electromagnetic radiation. So we can determine lots of factors about a star from their electromagnetic radiation. So to fully understand the radiation emitted by a star, we assume all stars are black bodies. Now it's a reasonable approximation to consider this particular idea. Now a black body is an object with a pure black surface that emits radiation strongly and in a well-defined way, and it absorbs all the light incident on it. Now they are black bodies because they do not reflect light. So a black body is a body that absorbs all electromagnetic radiations of all wavelengths and emits all wavelengths of electromagnetic radiation. Now you see the following result when you analyze a black body radiation curve. So you can see the following information of intensity on the y and wavelength of emission on the x. Now there are 3 lines for 3 different temperatures. This is because they emit all wavelengths of electromagnetic radiation in a continuous spectrum. So all black bodies have the same shape curved, but the curve shows that the hottest object has a peak at the shortest wavelength. Now this is a graph that links the intensity of the black body radiator output with the wavelength of the light. So like we said before, black body radiators are perfect emitters of radiation. They emit all radiation and they absorb all radiation, and stars can be thought of as black body radiators, which is indicated when we look at our own sun's emission spectrum and compare it to the theoretical black body radiation curve. Now the peak wavelength of radiation is linked to the temperature of the object. Now the higher the temperature of the object, the higher the peak wavelength of emission, the more shifted towards the blue end of the spectrum the object colour is. So this tells us that it is going to be more shifted towards the short wavelengths of the spectrum. So when the temperature of a black body increases, the intensity of radiation increases. It increases more so at the smaller wavelengths and shifts the peak wavelength to lower wavelengths. So what can we understand when we consider temperature and wavelengths of black body radiation? So when the temperature of an object increases, the intensity of all wavelengths increases, but this increase is greater for shorter wavelengths. So increasing the temperature of the black body radiator shifts the peak wavelength of emission to the smaller wavelengths. The peak wavelength determines the colour of the object, so therefore the hotter the object, the bluer the object will be. Now this is only true for emission. Now again, the cooler the object, the redder the object is. So hotter stars therefore produce more of their light at the blue-violet end of the spectrum and will appear white or blue-white, whilst cooler stars look red as they produce more of their light at longer wavelengths. Now if a cooler star emits more radiation in the visible than a hotter one, it will appear brighter, so just be careful about that. So a hotter black body will emit more radiation than a cooler one, and its peak wavelength will be a shorter wavelength. Now a hotter black body therefore will have a higher power output, assuming the same surface area. Now we can formalize it with a mathematical equation where lambda max is times by T equals 2.9 times 10 to the minus 3 meters Kelvin, which is the Wien constant. So this shows as the temperature increases, the peak wavelength of emission decreases. Now lambda max shows the peak wavelength of emission for a star. It determines the colour of the star. Now T shows the surface temperature of the star measured in Kelvin. Now it's a common examination mistake to think it is in Celsius. Now this particular equation indicates that we assume the star is a black body, and this is called the Wien displacement law. This law links the black body temperature with the peak of wavelength of emission. Now remember, the surface temperature of a star determines its colour, so this equation details the colour of a star also, and it is given to you in your examination equation book. So let's look at an example question with this particular equation. So if you wanted to work out an absolute temperature of a star, you would do lambda max times by T equals 2.9 times 10 to the minus 3. Make sure that it's in meters, work it through, and you get your answer out of the temperature in Kelvin. Now the power output of a star is the total energy it emits every second. So when we look at this particular idea, this is proportional to the fourth power of the star's surface temperature and directly proportional to the surface area. So we can formalize this with a mathematical equation where power equals sigma, the Stefan constant, times by A, the surface area, times by T, the surface temperature, to the power of 4. Now the Stefan constant is 5.67 times 10 to the minus 8, and this equation is called Stefan's law, and it is given to you with the constant in your examination equation book. Now this equation shows that the power output of a star is directly proportional to T to the power of 4 and the surface surface area of a star. So a cooler star needs to be a lot bigger to have the same power output. Remember, when calculating the surface area of a star, we assume the star to be a sphere, so the surface area is 4 pi r squared. Now remember, another term for power output is luminosity, so therefore Stefan's law also determines the luminosity of a star. Now it's a common examination mistake to think about what these particular values are without considering that power is actually luminosity. Now it's common in examination questions for you to determine the relative surface area of a star when compared to other stars with this equation. So again, we could look to work out what the power output of a star is if you're given a surface area and the peak wavelength. So you use the peak wavelength to find the surface temperature by doing lambda max times by t equals 2.9 times 10 to the minus 3. Then use Stefan's law, p at to the power of 4, to then work out the power. Now we can use the previous laws to compare two different stars. Now the law tells us that if two stars have the same blackbody temperature, the star with the brighter absolute magnitude has the larger diameter. Now although they have approximately the same blackbody temperature, for example Antares is one of the brightest stars and Proxima Centauri is one of the dimmest stars. So therefore it's not surprising to understand that the diameter of Antares is much larger than that of Proxima Centauri. We can also quantify the ratios of diameters of two different stars, because if the ratio of their power output was P1 over P2, then Stefan's law can be used to calculate the ratio of their diameters, D1 over D2, by rearranging your equation into having D as our subject and working it through as shown. The next thing we're going to look at is the use of spectral classes. Now as we know, a star is a blackbody radiator. This indicates that all stars should have a continuous emission spectrum as they are emitting everything, but we do not observe this with stars. We observe emission spectra and we observe absorption spectra, which is due to a property in atoms covered in the particles module. If you consider an atom with an excited electron in the fourth shell, we can then, for example, with electrons in the atoms of stars, like those in the atmosphere, okay, we've got to occupy certain energy levels or shells. So when this electron de-excites to either the third, the second, or the first shell, okay, they will therefore emit a photon of energy, a particle of radiation, which is equal to the difference between the two energy levels it transits between, and you can then use this to work out a wavelength by using the equation lambda equals hc over E, and we can do this for all particular energy levels and energy transitions. So what this leads to is an emission spectrum. So these are the lines for the radiation for the different possible transitions in the atom. So this links into stars because for a hydrogen absorption line to occur in the visible part of the spectrum, electrons need to be the n equals 2 state. Now absorption occurs when the atoms gain energy and the electrons move up energy levels. So in this case, what's happening is the electrons in the n equals 2 state for hydrogen are moving up energy levels. Now these series of lines are called Balmer lines. The Balmer lines are seen in all stellar spectrum when light emitted by the star has been absorbed by hydrogen atoms in the stellar atmosphere as the light passes through it. So the Balmer lines are very, very important because they are found in the visible spectrum of radiation. Now particles in the cores of stars do not contain electrons. It's only in the atmospheres of the stars where this effect takes place. So the Balmer line gives an indication of the surface properties of a star, not its core properties. Now as the Balmer lines can only occur in n equals 2, this is an excited state, this means the atoms must be at a high temperature where collisions between atoms give the electrons additional energy. If the temperature is too high, the majority of electrons will be in the n equals 3 state, so not many Balmer lines are produced. The intensity of Balmer lines depends on the temperature of the star. So when the electrons de-excite, the light is emitted in all directions and the electrons may do it in several steps or miss out n equals 2 and jump straight down to n equals 1. This results in a gap or reduction in intensity in the direction of the observer. Now if the temperature is too high, the majority of the electrons will be in the n equals 3 state, so not many Balmer lines will be produced. So the intensity of the Balmer line depends on the temperature of the star. So here we have a very low amount of Balmer lines at a high temperature because most of the electrons in the n equals 3 state. Here we have very few Balmer lines at low temperatures because most of the electrons in the n equals 2 state. Here we have lots of Balmer lines because the electrons are in the n equals 2 state. So the stars were originally classified in order of Balmer line intensity, with A being here, B being here, and C being there. But then it was realised it doesn't correlate exactly with temperature. However, the spectral class system had already been established by then. This meant we had to reorder the spectral classes in order of temperature, which is why the spectral classes are not in alphabetical order. Now, in addition, for particular Balmer line intensities, two temperatures are possible by looking at our curve. So to get around this, you've got to look at the absorption lines of other atoms and molecules. So this class of a star depends on the relative strength of the different absorption lines. So this means for stars with temperatures outside Balmer line transition transitions, we've got to use absorption lines of other elements, as shown in this particular diagram. Now, it's important to note that the link between surface temperature and spectral class is evident because these will affect the absorption lines produced. So again, the surface temperature also links to the colour, so the colour and the spectral class are intrinsically linked. Now, it's also important to note that the relationship between temperature and spectra is due to the effect of the energy on the state of the atoms of the molecules. Now, at low temperatures, there may not be enough energy to excite atoms or break molecular bonds, resulting in molecules found in the spectral lines of the very cool stars. Now, at higher temperatures, atoms have too much energy to form molecules and ionization can take place, so you can see absorption lines of ions. Now, the abundance of hydrogen and helium in the atmosphere of the hotter stars means that spectral lines start to dominate, and the hydrogen Balmer series is a useful indicator here. So you can see here our different spectral classes. We've got class O as the hottest, then B, then A, then F. Then we know that this tells us that white dwarfs, which are in the F class, must have a higher surface temperature than red giants and main sequence stars. This occurs as the intensity of their emission is so large as their surface area is so small. We then go to class G, which is where the sun is found. We then go class K, we then go class M, and these stars are cool enough for molecules to form in their atmospheres. This means red giant stars have the lowest surface temperature of all stars. This occurs as the intensity of emission is so low that their surface area is so large. Now, you should know that the stellar classes from hottest to coolest is O, B, A, F, G, K, M, and you can use different mnemonics to remember this particular order. Now, since the original classification, further cooler stars have been discovered and given classes, but these are not required. So for your stellar classification system, you've got to learn the different properties for your examination. Now, you've got to be able to estimate temperature and colour if given a class, and you've got to be able to recognise class if given an absorption spectrum. Now, the colour change links to the temperature due to the Vine displacement law, and we can also classify the stars due to Balmer lines. Now, the next thing we're going to look at is the Hertzsprung-Russell diagram, as in 1911 it was realised if we plot spectral class against the absolute magnitude of stars, the stars can be collected into distinct areas. So it's in essence a plot of luminosity of the stars against their surface temperature, and you can work out a great deal of information. So as surface temperature is closely related to spectral class, that can also be placed on the x-axis. So the y-axis is a measure of the brightness of a star. So what we know is, because of the scaling system, is a very negative number at the top and a very positive at the bottom, and you've got to remember it's from -10 to +15. The x-axis is a measure of surface temperature from very hot to very cold, so 50,000 to 2,500 in a non-linear scale. So it's very hot on the left, very cold on the right, so the temperature is scaled to the opposite direction you would expect. Now, this scale can also be represented with spectral classes with O to the left and M to the right, which leads to the following areas on your Hertzsprung-Russell diagram. You've got bright and hot top left, dim and hot bottom left, bright and cool top right, and dim and cool bottom right. So we can place our observed stars in the following areas. So they're not randomly scattered, so they're leading the following groups. So it can be approximately the power output of all these stars is the same. So you've got the main sequence, white dwarfs and red giants. Then you've got to place two particular stars in the main sequence. You've got the sun here and you've got Vega here. Now the main sequence is where you have your long-lived phase of your star life, where hydrogen is fusing into helium, which is where the sun currently is. Now, approximately 90% of stars are on the main sequence, and at the top of the main sequence are the hot, luminous blue stars, and at the bottom are the cool and dim reddish stars. You then got the red giants and super red giants class, which suggests that these stars are bright but cool. You've got to recognise that Betelgeuse belongs here. Now, because of P equals sigma AT to the 4, the red colour suggests a low temperature, so for a constant power output, the area must be large. So it's also important to note that this is how we know that these particular stars must be giants. Now, red giants are stars which have moved off the main sequence, and fusion reactions other than hydrogen to helium is happening here. Now, supergiants are approximately 10 to 100 times larger than the mass of the sun, and are substantially more larger and more luminous than even red giants. Now, supergiants are hot enough for nuclear fusion to produce carbon and the heavier elements. You've now got white dwarfs, which suggest they're in a region where they are hot but dim. Now, P equals sigma AT to the 4 suggests that the white colour means there's a high temperature. To maintain a constant power output, the area must be small, so this must be a dwarf stars. Now, white dwarfs are the stars at the end of their lives where all fusion reactions have stopped and they are slowly cooling down. So these become the end state of the low mass stars once they become black dwarfs. Now, the significance of the Hertzsprung-Russell diagram is it tells us they exist fundamentally different kinds of stars due to the fact that there is a stellar life cycle. So astronomers have worked this out and have understood that stars are born, they then grow old and they die. So we can see for an average sized star that the stars on the main main sequence, and the placement depends on its size. It will move slightly up the main sequence, but not completely up the main sequence, go across to the red giant stage, its placement dependent on its mass, and then it goes to a white dwarf where once again its placement is dependent on its mass. So we can see here or here in these particular diagrams. Now we're finally going to look at supernovae, neutron stars and black holes. Now a stellar life cycle of a star begins with a planetary nebulae. So hydrogen nuclei which were produced after the Big Bang are collected in a large area called a nebulae. Now the original name for a nebulae was a planetary nebulae, but there are no planets in a planetary nebulae. Now a nebulae is a very cold region of space, and the gas molecules are moving very slowly. The denser clumps of the cloud contract very slowly under the force of gravity, and this then produces a protostar. So the gravitational attraction takes over and pushes the particles together to form a sphere. So this sphere is called a protostar. So it goes from nebulae to protostar. So as the clumps of hydrogen and helium come together, the density of the area increases and the particles hit each other more. This causes the sphere to heat up. The temperatures increase inside the protostar, but it's still too cold to carry out nuclear fusion. So gravity forces hydrogen into sphere as it's the most stable shape in the universe. Now eventually the temperature and pressure of the protostar increase so much that fusion begins. So at this point the protostar becomes a star. The star starts to release radiation via fusion, and this creates a pressure to stop the gravitational collapse taking place. So when a star carries out hydrogen fusion, it is in its main sequence, shown here, which is the first time when it appears on the HR diagram. Now during the main sequence, hydrogen is fusing together to form helium. So when this happens, the mass before is greater than the mass after, so some of the mass of hydrogen turns into energy, which then releases energy as radiation with the particular equation E equals delta mc squared. Now on a main sequence star, there are two forces acting upon it: the gravitational attraction produced by the mass of the particles in the star acting inwards, and the fusion pressure produced by the products of fusion escaping the star acting outwards. Now in the main sequence, fusion pressure equals gravitational attraction. Now because there's no overall force on the star remains stable in its main sequence. So this shows us that the greater the gravitational attraction in a star, the greater the fusion pressure required to gain equilibrium. This means that larger stars have a greater rate of fusion compared to smaller stars. This means that larger stars have a greater rate of fusion compared to smaller stars, so spend less time on the main sequence than smaller stars. So because our Sun is quite a small star, it will only spend a long time on the main sequence compared to other stars. Now this stage can also be called hydrogen burning, because our star is very stable and unchanged due to the balancing of the forces due to our core hydrogen fusion taking place. Now when the hydrogen runs out, heavier elements then begin to fuse, and it causes the star to expand to a red giant. This is the next phase of our particular life cycle, which is shown at this point on the Hertzsprung-Russell diagram. Now in red giants, fusion of elements larger than hydrogen takes place. So when all the hydrogen in the core has fused to helium, nuclear fusion stops, and with it fusion pressure leaves. So as a result, this causes the core of the star to contract, and then it heats up. This increases the temperature of the core. This makes the star hot enough to carry out fusion of helium and heavier elements. This increases the size of the star as the fusion pressure is now larger than the gravitational contraction, so therefore you've got your larger star. So the star increases in size and becomes a red giant. Now we've learned this before, that the temperature of a red giant is lower than a main sequence star, as even though it produces a greater amount of energy, it is more spread out. So as the surface area of the star is larger, to maintain a constant power output, the temperature must be lower. Now more energy is needed to fuse larger elements together, as there's a greater repulsion between them, because larger elements have more protons, so a greater positive charge. Now the energy found in a star is proportional to its core temperature. Now there's not enough energy to fuse elements larger than carbon in average stars. They're just not hot enough. Now stars also carry out shell fusion of elements. So in a red giant, there are several fusion processes taking place simultaneously. So in reality, you've got several processes that are taking place. Now the fusion of the heavier elements takes place in the core, as it requires a larger pressure, since the nuclei have a greater positive repulsion. So the lighter elements can be fused on the outside because they need less pressure. In addition, the radiation from fusion in the core heats up the outer layers to allow the temperature in this part to carry out fusion. So our star contracts, heats, and then fuses successively bigger nuclei in its structure, and this idea is called core burning. But you've got shell burning on the outer layers of our star. So you have core burning in the middle with shell burning on the outside. Now we think our Sun will go red giant and the Earth and the inner planets will be destroyed. Now eventually fusion stops as the temperature and pressure are not high enough for further fusion. The outer layers drift off and a white dwarf is formed. So the outer layers are then released to form a new nebulae to start the cycle. This occurs as the core temperature of the red giant is not large enough to fuse heavier elements together. This causes the star to shrink under the force of gravity. This then makes the shell of helium around the outside unstable and the shell is ejected. Now the core of the star eventually stops shrinking due to electron degeneracy pressure as the electrons repel each other to exist in shells. So this leads to white dwarfs forming, which is the last stage of our average size star, which is found in the following part of the Hertzsprung-Russell diagram. So after the fusion processes are stopped, the core of carbon is left behind, which is a white dwarf. So it could be considered a core of diamond. Now the white dwarf is like a hot ember after a fire. This dwarf will cool down for a long time as energy is lost to space. Now a white dwarf must have a high temperature, so because of P equals sigma AT to the 4, so if A is very small, T must be very high to maintain a constant power output. Now eventually the white dwarf cools down until a black dwarf is formed. This happens as radiation is lost to space. Now black dwarfs have never been observed in the universe. They are purely theoretical objects. Black dwarfs are in thermal equilibrium with space. They are very cold. They have never been observed because they're very small, very dim and exert little gravity, so cannot be easily observed. In addition, the universe has not existed for enough time for a black dwarf to form from a white dwarf. So we've got our stellar evolution. Well, what about a larger star? So for a large red giant, what happens is you get many elements forming via fusion in the red giant, because larger red giants have stars with temperatures and pressures which can fuse up to the element of iron. So it's important to know that our red giant has many different layers. Now fusion cannot occur above iron because iron has the largest binding energy per nucleon of any nuclei in our universe. So the heavier elements are found in the core of the star and the lighter ones in the shells around the core. But eventually when you get to iron, the fusion stops and therefore the gravitational force inwards is unopposed, which causes an implosion. So the unopposed gravitational attraction causes the star to implode into its core, and this implosion increases the pressure and temperature of the core to produce a cataclysmic explosion, which is a supernova. Now this explosion distributes all the elements produced at the red giant stage into space to form a new nebulae, so it starts the stellar cycle again. Now the temperature at the core during supernova is thought to be 100 billion kelvins. So this energy will only last for a short amount of time, but in this period the production of elements heavier than iron can form. So these are the only conditions found in the universe where we believe elements larger than iron form, as shown here. So a supernova is not covered in the stellar life cycle is not covered in our Hertzsprung-Russell diagram. So you can see in this particular image that one supernova has a luminosity which is similar to 1 trillion stars. So when a star undergoes supernovae, it will experience a brief and rapid increase in absolute magnitude. Now the energy of a supernova is 10 to the 44 joules, and we call this type of supernovae a type 2 supernovae. This is not the same as a type 1a supernovae, which all have the same luminosity, so it can be thought of as a standard candle. So the defining characteristic of a supernova is that it's a rapid massive increase in absolute and apparent magnitude, and we can represent this change in absolute magnitude with a light curve. So this is a light curve for a type 1a supernova, which you've got to be able to recall. There's a sharp initial peak followed by a gradually decreasing curve. Now you've got to be aware of the different axes values for absolute magnitude and time. Now you'll notice that the peak is at -20, so you've got to note that all type 1a supernovae follow the same curve, so therefore can be used as a standard candle. So type 1a supernovae occur when a white dwarf absorbs matter from a nearby binary star, which causes the white dwarf to explode, and as the explosion is produced with the same level of mass, they produce identical light curves. Now there are many types of different supernovae which can produce different light curves. Now type 1a supernovae have no Balmer lines, but type 2 supernovae do have Balmer lines in their absorption spectrum. Now type 2 supernovae can produce more energy than type 1 supernovae, and this takes the form of gamma rays, so it's called a gamma ray burst. Now a gamma ray burst can last for minutes or very rarely hours, so it can produce lots and lots of energy. So you can see in these images gamma ray bursts. Now if a gamma ray burst occurred relatively close to the Earth and was directed towards the Earth, it would destroy the ozone layer, which could lead to a mass extinction event. So we've been very fortunate that no GRB has occurred close to the Earth. So when a supernova occurs, you definitely create a nebulae, but there are two possibilities as to what else could exist. You could produce a neutron star, a star completely comprised of neutrons. Now there's little empty space as the neutron star has a nuclear density, not an atomic one. So it has a density of 4 times 10 to the 17 kilograms per meter cubed and a diameter of 20 kilometers. So this means it has a very high density and an extremely large gravitational field. The speed is so high, almost the speed of light. Now neutrons cannot be compressed any further and form a neutron star because, as we know, the strong nuclear force becomes repulsive at 0.7 times 10 to the minus 15 meters. So this idea is called neutron degeneracy. Now, because it's produced in a supernova explosion, a neutron star must conserve momentum, and to do this, many neutron stars rotate about their axis up to 600 times per second. Now, when this happens, it will emit radio waves in a set of narrow bands as shown in this particular animation. So you can see that the radio wave beams can sweep past the Earth in regular pulses and can be observed like flashes of a lighthouse. So we call these objects pulsars. But if the core of the compressed star is so large that the gravitational field is so strong that not even light can escape it, it is in fact a black hole. Now, after a black hole is formed, it can continue to grow by absorbing mass from its surroundings, and by absorbing other stars and merging with other black holes, supermassive black holes of millions of solar masses can form. So a black hole is a neutron star which is so massive and dense that its gravitational field does not let electromagnetic waves leave it, so nothing can escape it. So it appears black, so it's a black hole. Now, either a black hole or a neutron star is produced at the end of a larger star's life cycle. Now, technically, a black hole should evaporate slowly over time. Now, there are two sections to a black hole: the singularity, which produces the gravitational well, and the event horizon, which is the closest you can get to the black hole before you can no longer escape. The distance between the two is the Schwarzschild Radius. The Schwarzschild Radius is the distance at which the escape velocity of an object is equal to the speed of light. It's the effective radius of the black hole. So if we consider thinking about our ideas of gravitational potential from the gravitational fields topic and the gravitational potential energy equation found from that particular topic, we are aware that actually we can say that the energy needed to gain out of a black hole is minus gmm over r, but that needs to be found in terms of kinetic energy, so we can equate the two to each other, rearrange it and make r the subject, and this gives us our equation for the Schwarzschild radius. R equals 2gm over c squared, where r is the Schwarzschild radius, g is the gravitational constant, m is the mass of the black hole, and c is the speed of light, which again is an equation given to you in your examination book, and this derives the minimum distance between the singularity and the event horizon of the black hole. The more mass of the black hole, the greater the size of the black hole. So let's summarize what we've learned. We've looked at apparent magnitude, the Parker scale, dimmest visible star have a magnitude of 6, and the relationship between brightness and apparent magnitude, which is the idea that brightness is a subjective scale of measurement, and the difference of 1 on a magnitude scale is equal to an intensity ratio of 2.51. We know that m minus m equals 5 log d over 10. 1 astronomical unit is the distance between the Earth and the Sun, 1 light year is the distance travelled by the light in 1 year, and 1 parsec is the distance at which the observed parallax angle is equal to 1 arcsecond. We should know Stefan's law and Wien's displacement law, the general shape of blackbody curves, the use of Wien's displacement law to estimate blackbody temperatures of sources. Experimental verification not required of this, but lambda max times by t equals a constant. We assume a star is a blackbody, we can use the inverse square law, and we can use Stefan's law to compare power outputs, temperatures, and size of stars with p equals sigma at to the 4. We should know the description of the main stellar classes, and that temperature is related to absorption lines linked to the hydrogen-Balmer series when the atoms are in the n equals 2 state. We should know the general shape of a Hertzsprung-Russell diagram with main sequence, dwarfs and giants. We should know the axis scale range from minus 10 to plus 15 in 50,000 Kelvin to 2,500 Kelvin, or use the spectral classes. You should be familiar with the position of the Sun on the Hertzsprung-Russell diagram and the stellar evolution, the path of a star similar to our Sun on the Hertzsprung-Russell diagram from formation to white dwarf. You should know the properties of a supernova, including its rapid increase in absolute magnitude and the composition and density of neutron stars. Know the escape velocity is greater than the speed of light for black holes. Know that gamma ray bursts due to the collapse of supergiant stars form neutron stars or black holes. Compare the energy output with the total energy output of the Sun. Use type 1a supernovae as standard counts to determine distances, and understand that the idea of the light curve of a typical type 1a supernova, we have supermassive black holes at the center of galaxies, and the calculation of the radius of the event horizon for a black hole, the Schwarzschild radius, is equal to 2gm over c squared. So I hope you've enjoyed this revision session on stars, which is part of the astrophysics topic in AQA A-Level Physics. Thank you very much for watching, and have a lovely day.